Here we are at example 1 from our 2.7 set of notes. We're asked to find the derivative of y with respect to x for this particular function at this specific target point. Now, with this specific function in mind, we actually would end up with two y values, and that's why we actually have to use implicit differentiation at this particular point. So what we're going to do is do step 1 according to our steps for implicit differentiation. We're going to take the derivative with respect to x on both sides. So again, take the derivative with respect to x on both sides. And as a result, you would end up then with taking the derivative with respect to x of the left side, x squared plus y squared is equal to the derivative on the right side. So the derivative with respect to x of 4. Now, we've actually done this in our previous set of notes earlier in the chapter, but we didn't necessarily go ahead and do this step. Now, the reason why we are is because we are conducting actually implicit differentiation. So it's really important to actually kind of show what's going on with these different variables. Whereas before, when you took the derivative on both sides, but you ended up with like y prime or f of x, f prime of x. So you were still taking the derivative with respect to x on both sides. Now, when we go ahead and actually take the derivative of our left side, we're going to apply it to both items. And again, we're taking the derivative with respect to x. So we have the derivative with respect to x of x squared plus the derivative with respect to x of y squared is equal to the derivative with respect to x of this constant 4 will just come out to be 0. Now, when we're looking at this first derivative, believe it or not, there is in fact an embedded chain rule actually happening here. You can see that your outside function would be this squared term, and your inside function would actually be x. And so when you actually apply the chain rule for this x squared, you would end up with 2x. So you took the derivative, in other words, brought that exponent to the front, subtracted 1 from that, so we have 2x to the 1, but then you're also taking the derivative of your inside function. In this case, it would literally just be x. The same thing is going to happen for our y. So then we have plus 2y, again, just using your power rule, subtracting that exponent by 1, but then you're also taking the derivative of your inside guy. So the derivative with respect to x of y. So believe it or not, these are chain rules actually happening behind the scenes. Is equal to still 0. Now, just simplifying this up a little bit, we see that we have 2x to the first times the derivative of x with respect to x. So that would be dx over dx plus 2y to the first power. Same thing's happening here. The derivative of y, in other words, dy over with respect to x. So dx. And that's equal to 0 still. Now, typically the reason why we didn't just necessarily show a chain rule happening when we were taking like the derivative of like x squared, and a lot of times we just kind of thought the power rule here because it came out to be just 2x, but we didn't really necessarily show like that dx over dx because in the end this will just come out to be 1. And as a result, for this piece right here, this dx divided by dx, that's literally just 1. So we end up with 2x to the first times 1 plus 2y to the first dy dx. And that's still equal to 0. And the reason why I really wanted to show that with the x squared is so that you guys can actually see that it does in fact transfer through. But more specifically, it transfers over really well in finding exactly why the dy over dx actually works. So believe it or not, these are in fact chain rules happening behind the scenes. Now we would end up then with 2x plus 2y dy over dx is equal to 0. I kind of just dropped the exponents because we didn't really need to write them. And now our goal is to solve for dy dx. So now we're in step 2. We've taken the derivative with respect to x on both sides. Now we're in step 2 where we want to solve for dy dx. And how we would do that is we would first try and isolate our dy dx by subtracting 2x from both sides. So when we do that, we end up with 2y dy dx is equal to negative 2x, dividing both sides by 2y. We would end up with them canceling on the left side, leaving us then our dy over dx is equal to, it appears that our negative 2 would cancel out with our 2, leaving us then with negative x on top over y. So there we've gone ahead and solved for our dy dx. Now step 3 says to substitute your x and y into the equation to figure out your tangent slope. Because again, your dy dx, your derivative of y with respect to x, is in fact your slope, your tangent slope. And as a result, we can then go into step 3 and substitute in our x and y. So again, this is step 3. So it looks like our derivative of y with respect to x comes out to be our target point was 1 comma negative root 3. So negative 1 divided by negative root 3. Now just simplifying this up a little bit, we see that our tangent slope comes out to be negative divided by a negative is a positive, so it looks like 1 over root 3. Just rationalizing this, you would do a little bit of foo, so root 3 over root 3. So then it looks like our derivative of y with respect to x comes out to be the square root of 3 over 3. And again, this is our slope of the tangent line when x is 1. And again, that's that target point to 1 comma negative root 3. But again, that is example 1 from our 2.7 set of notes.